treat it differently. Sustainable chemistry, if you really think about it, requires you to shift the way you think about chemistry, as I was mentioning. Systems level thinking is something that chemists don't really think about. That is we have to see everything in the big picture. Once again, from raw materials extraction to end-of-life considerations. And unfortunately, we don't. We generally just focus our attention on what we do in the laboratory and that we are able to do chemistries to get our drug substances out the door. Use-inspired, that is that many chemists don't practice chemistry as though it has a practical application. They do chemistry for the sake of chemistry. Efficiency is one that's really interesting. I won't go into that very much, but we really have to think about conservation and efficiency that go hand in hand. The essence of Jevons paradox is that when you make it more efficient, you use more of it. And there's a huge number of examples of that being the case. Finally, the sustainable chemistry really requires a multidisciplinary approach to chemistry. We as chemists and chemical engineers tend to be very siloed in how we think about chemistry and chemical engineering. So there are a lot of challenges that you face. I know I'm preaching to the choir here. There are infrastructure challenges in terms of in-ground capital that is there. The economics and financial analysis to move to something new is quite difficult. The current business climate has not been terribly favorable for investment. But I would argue that the biggest problem that most of us face in changing things within how we do things is really a societal or a behavioral one. And changing the way people do things like chemistry and chemical engineering is one of the hardest things that we face. This is just an example. If you look at the kinds of reactions that are used every day by chemists in the laboratory, most of those reactions were discovered quite a long time ago. Add that up, and I often talk or quip that when a chemist comes up with a truly novel way of doing chemistry, they win a Nobel Prize nowadays. That's how rare it is. The majority of the chemistry which is practiced is based on precedent of chemistries that were discovered 70 to 100 years ago. And we really need to change that paradigm. We need to have a different set of reactions in our toolbox because our chemistries are highly inefficient. If you're a chemical engineer and you say, well, gee, I don't have to worry about things because we're much better, if you walk into a modern plant, you'll see something like that, an impeller, but it'll maybe be in a stainless steel reactor. But that kind of thing came into being a long time ago, so let's just have a little fun here. When did a batch reactor start getting used? That was the Bronze Age. Distillations really took off to encourage the gin trade. And crystallizations was also a Bronze Age innovation. So the basic ways in which we process things really has not changed. We're beginning to see the use of flow chemistry, and we're beginning to see things more in the batch industries moving towards something that looks more like a petrochemical kind of efficiency, but we're still light years away from that, to be perfectly honest. I also understand that the current batch chemical process development is really quite complicated. Large portfolios, significant route modifications, complete substitution, focus on yield and quality. We do these things because they're thermodynamically favorable, but there are these risks that we have with the materials that we use. So I'd like for you to think a little bit about design, because if you're not thinking about design and doing things from first principles, we're never going to make a change. And we need to do early design evaluations often. And finding this commercial balance between speed to market and attrition, it's very difficult. You have the 12 principles here. We've reduced them down to 3 because we find that most people can't remember 12, but they can at least remember 3. maximizing resource efficiency, so the materials that we use, the industry is very inefficient. Most process mass intensity around most drug substances is less than 1% efficient, right? 99% of it we throw out. Eliminating, minimizing hazards and pollution, we still use a lot of materials that will kill us. And so we need to think about doing chemistry in a different way. Designing systems holistically and using life cycle thinking is another thing that we need to do. So I'll just speed through these. Really the key to green chemistry is always and always has been about innovation. We need to innovate our way out of our current situation. Green chemistry, if it's being practiced correctly, has an environmental preferability to it, an economic viability, and societal need. And I think that's the hope for the future, is that green chemistry really does meet all of those needs. Green chemistry innovation really shouldn't look any different than any other kind of technical innovation, right? And so it should be able to help you achieve top-line growth and cost reductions, overall risk reduction, tremendous amount there, and a lot of intangibles. Doing things in a way which are not creating hazards or creating environmental devastation really does help in terms of public perception. This community right to operate is extremely important, because it's an industry that arguably has some issues associated with how it's operating. You could also think about it from a cost strategy perspective, so low-cost supplier. The thing about green chemistry, if you're doing it correctly, if you're doing your processes from a green or sustainable perspective, it is going to be, by definition, the low-cost route. It's going to be the low-cost manufacturer, lowest cost producer. It also will allow you to differentiate yourself in the market. We need innovations virtually everywhere, not just in manufacturing, but in the laboratory. So moving the types of things that chemists do in the laboratory towards a more continuous mode. Chemists and engineers need to work more closely together. Our business processes need to think about valuing things that are beyond just what's in the laboratory or in our manufacturing facility, but thinking about the broader context in which we operate and valuing things that we're currently not really paying for, like the air or the water or the land. And other resources really need to change. So there needs to be a lot of education that takes place, because staff really is not educated to think about green chemistry and how to do that. There are a lot of financial benefits. If I had a lot more time, I would give you case studies of where companies are making a play in green chemistry and doing well with it. Best practice, there are a few key metrics. If you're not measuring, you can't manage it, and these are the kinds of metrics. I'm just going to cycle through these that if you're a process chemist, you know and would want to use. Many of you will say, gee, why can't I use yield? It's because yield really will not get you what you want. It's a very poor measure from greenness, from a greenness perspective. Again, if I had more time, I would talk more about that. We need to, again, extend the envelope of how we're doing our reactions, where we do them, the reaction spaces that we use. In the medium term, we need to get to this more efficient processes on a regular basis, substitution of materials that are good, inherently good or better, sustainable technology, easier technology transfer, routine mass efficiencies, 5 to 10%. Right now, we're just at, again, about 1%, protective of people and life cycle routinely considered. In the longer term, lower cost, less energy, less resources, inherently less hazardous materials, less waste, and with that will come this improved profitability, lower prices, and this use of renewable resources and biological systems. My personal view is that chemistry is going to look more biologically enabled than it does now. In other words, synthetic biology should be the chemist's friend in the future, not something that they don't understand. So I think that you appreciate that the sustainability risks facing the industry are really quite large, and we really do need to do something about it. Green chemistry oftentimes is just concerned about hazard reduction or elimination and pollution prevention. It's really much broader than that. It has to be. Innovation is clearly the way that we're going to solve our problems. We need to innovate our way out of our problems. I think that the pharma and specialty industry is uniquely qualified to really make this change, much more so than the petrochemical industry. I mean, the petrochemical industry is not sustainable by definition. So pharma and specialties really have an opportunity to lead the way. Early design is extremely important. And finally, there are a lot of tools. That's one of the reasons the Pharma Roundtable exists and is such a profound collaboration, is the tools that they've developed over many years. And that's really what we'd like to see more happen in this part of the world, is that chemists beginning to use these tools to make chemistry and manufacturing processes greener. And I think with that, I'm probably way over my time. Shameless plug for our conference. There are a lot of conferences now in green chemistry and engineering, and just encourage you, if you don't come to ours, attend one. There's one the Australia Royal Society of Chemistry is putting on in June. There's lots of opportunity to attend conferences. And I think I should just turn it over to the next speaker. So thank you very much for your kind attention.
Thank you. So we have some time for a couple of questions. Yeah. If you could just introduce yourself then.
Yeah, hi, I'm Yasir Raoji from Milan Laboratories. The question I have is that when we are looking at chemistry and chemical transformations, is there a toolbox out there, right, that we can advise our people to refer to, as an alternative, right, to achieve a chemical transformation? I mean, is there, what I'm trying to get at is that, one is, have we invented, green alternatives for all chemical transformations? Obviously, the answer is no, right? But what is out there, right, and what can be made, commercially sustainable is something that, we'd like to get our hands on. So where do we go?
Okay, so the Pharma Roundtable actually has developed a number of tools, and Juan will be talking about them. But for example, a solvent selection guide. So solvents are extremely important to the pharma industry. You can make better solvent selections. That's a real, in my opinion, that's a real easy win. They've also developed a reagent guide, which helps, you do a bunch of different routine chemical transformations. Some reagents that you use are better than other reagents. And so they've put together this guide to help chemists understand, and that's available on the internet. They routinely publish twice a year in Organic Process Research and Development a compendium of the most recent green chemistry innovations in the literature. So there are these things that they are doing on a regular basis to try and help chemists make better decisions about their chemistry.
Thank you.
I can help you a little supplementing your understanding. There are advancements like for enzyme screening. You get the plates now. You just put a drop of the reagents. You can choose which is the best enzyme for the conversions. You have reductases, hydratases, all those. It's been there in the commercial market. For chiral separation, for chiral synthesis also, for the chiral reagents, there are plates available now. You don't have to try, like the salt screening is said, you have the carousels. Similarly, you can do the chiral synthesis. So at one go, you can find out A, the synthesis, and B, even the separations. They are there in the market, commercially available.
There's also a site, I should have mentioned this, that the Innovative Medicines Initiative in the EU put together a very good site to educate people, and that also is available. It takes people through metrics, it takes them through solvents, it takes them through various aspects of process development, and that again is available on the web.
Okay, so are there any more comments, questions? Okay. Dr. Sudhir Nambiar there.
I'm Sudhir Nambiar from Heikel. My question is, you mentioned about structural biology, and now with a lot of gene editing techniques coming out, I think overall the advances in biology seem to put the advances in chemistry in the shade a little bit. I mean, it looks like, there's far more advances in biology that will benefit chemistry than chemistry to benefit chemistry. So you have any comment on that? Because, when you look at things like CRISPR, you can see that you're moving closer to God in certain ways. So, I mean, you mentioned about the paucity of innovation in chemistry when you look at it in a case, whereas biology seems to be moving forward by leaps and bounds. Would chemistry be finally, just a kind of service provider for biology going forward? I mean, we are focusing a lot on green chemistry, but I think interdisciplinary is going to be very, very important going forward.
Yeah, no, I would agree. I mentioned a lot about platinum group catalysis, and so that there are three alternatives